Narrative number 3, I will continue to look at the posture correction software and specifically how recent revelations have made research applications significantly more viable and as well as a much easier option for me to pursue. So the results of the jawline recognition research are the first thing I want to look at, specifically from my project journal that I recently submitted, as well as elevator pitch, which showed these polygon bounding boxes, which I'd used to do a much more simple program where a program would just simply have to recognize the jawline. And so I used Jupyter Notebook for model training because it is the model training service that Always AI directs to, which was the model training toolkit I was using. And as you can see, the model loss on the right is actually X'd out because when I tried to run this procedure, I'd found out something significantly more important about model training, which is that it can't be done on local devices or more mobile-like devices, such as a basic laptop or an actual mobile device, and actually requires significantly much higher computing power. And so what I was actually looking for was inferencing. And so to expand on that, let's go a bit deeper into what model training is and how we can proceed. So model training, even though I was unable to do it, the main reason for that was that training loss, which is shown by the red arrows in the images here, is actually what needs to be reduced, and that is how models actually train. So they create that blue line is sort of their estimate, and they shift their estimate so that the image moves from the image on the left to the right, such that the red arrows, which begin at random points, slowly become as minimal as possible for all points of the data. And so that is how the model will know when to stop. And so when looking at deep learning specifically, because that is what I will eventually be transitioning into now, considering that basic machine learning algorithms are decently weaker, and for specific research, I would like the training program to be much stronger. It can be split into two parts, which are training and inference, and the training process is computationally much more expensive. And so that means that it can't be done mobile-like devices, and actually has to be done on desktop computers and or servers that are much more capable of handling these complex calculations because of the severely high number of calculations that needs to be done for a training loss. So taking a step back in order to take a few more steps forward, I think that it would be much better to delve into what neural networks and deep learning actually are, since I will now be transitioning into them. And so neural networks are a set of algorithms that are designed to recognize patterns. They interpret sensory data through machine perception, and machine perception is like a labeling or clustering raw input, and that's how it kind of takes everything in. And the patterns that they recognize are numerical, contained within vectors. And that's how they take in all real world data, including images, sound, text, etc. And so with classification, deep learning is actually able to establish correlations between pixels and a human face. And that is what's known as static prediction. And so to build off of that, if given enough data, then deep learning, which is actually just a way to identify stacked neural networks or neural networks with a severely high amount of layers, and their efficacy is kind of seen by the depth of those neural networks. This sort of deep learning can actually be used to kind of predict future events or compare current data to predicted data and then use that as a way to improve the model. And so specifically, the network models I'll be talking about for deep learning strategies, because those are the most prevalent facial landmark detection, those will almost always be convolutional neural networks. And so looking at my project, the main mistake I'd been making previously was that, as seen in the polygon boxes, I'd simply been trying to recognize if a jawline exists. However, if I do actually want to analyze the mastication muscles within the jawline as well as the mandibular jaw, then I will actually need significantly more accurate depth of the points on the jawline, which is done through landmark detection. Landmark detection, there are three main ways this occurs: through holistic methods, constrained local methods, or regression-based methods. And because of my previous explanation on how deep learning and convolutional neural networks work, I found that regression-based methods are the most effective and the easiest because that's also what has been used the most for landmark detection. And additionally, I would need to combine this with posture as pose estimation because of my previous posture algorithm, which utilized the eyes, nose, ears, etc. And those were significantly more basic points, which did not necessarily be as detailed as the landmark detection will need to be for my jawline. So I'll have to combine these two things. But how will I be able to do that? The change of scenery that you depict here, these are actually known as cascades. And the reason that they're depicted is because of cascading regression. Cascading regression utilizes cascade classifiers, which allow for cascading through data. And so what it basically does is it creates a bunch of situations where an image is put through layers of yes or no's. And these binary decisions create a sort of gray area of a maybe for a machine learning model. And eventually, if an image can pass through all of the cascades, then success is initiated. And if the image does not pass through any one of the layers, then it immediately gets discarded right there and then, which allows for increased efficacy, which will be extremely important in creating a much lighter machine learning model, which is what I'm going to have to start, which I'm trying to research further into. So the reason for this is that the classifiers do not approve the image unless it already has approved everything before it. And this is kind of what reduces the intensity. So the reason that this is so important, cascading, is because that's how I actually used to pick a deep neural network for my further research. And so what you see here is a table that was used from previous research on a number of deep neural networks that are actually viable for use on mobile devices. And the reason this is so important is because I also had to look for deep neural networks that would actually not be extremely intensive, because that would be a way in which I could use my actual posture training, because if it is too intensive, then I would not be able to carry it out. So specifically when looking at these, the DAN is the deep alignment network. And the deep alignment network is also very good because the only way that I found that I could connect landmark detection with pose estimation is through cascading, and DAN actually uses cascading. So the deep alignment network uses cascading coordinate regression, meaning it puts coordinates, but it also uses heat maps, which are basic areas where the machine learning model should focus, in order to connect those cascading layers. And so it uses a full face recognition, as you can see from the image on the left, and it uses the heat maps for precise landmark detection, which is beneficial to my project because that's exactly what I'm trying to do. So the difference between direct regression and cascading regression, as this network shows, is that cascading regression uses initial guesses and then improves that through multiple stages. So it creates a much higher accuracy level, as well as starting off with something that's much easier to implement as well. So the reason that the deep alignment network is so important is because it is the most effective combination of the deep neural network constraints that I have, which include trying to create a model that is significantly less intensive, even if it might sacrifice a slight amount of accuracy, as well as creating a sort of cascading regression model, because that is the only model where you can take the human pose estimation and combine it with landmark detection. And so for this reason, my further research will have to be required to test whether this actually is a viable process of combining cascading regression previously in other research with this research regarding the deep alignment network in mobile applications. And if this research is possible, how I can apply that to my own posture correction model and create a working blueprint for how that could actually come about.